Good day, everyone. Most organizations start with monolithic architectures. Over time, their customer base increases, data complexity increases, and also the teams grow. This brings its own set of challenges. We at Confluence Cloud ran into similar challenges, and I would love to share our journey of evolving Confluence Cloud for scale, reliability, and performance. My name is Bhakti Mehta, and I'm the Senior Chief Architect for Confluence Cloud at Atlassian. I've been working at Atlassian for 8.5 years. I'm an author of 2 books and a regular conference speaker. For my past experiences, I have been a platform lead at Blue Jeans Network, which was a video conferencing platform in the cloud. Before that, I was at Sun Microsystems and Oracle for 13 years. The following are my 2 books, emphasizing on building scalable, reliable, and maintainable applications using RESTful web services. So without further ado, we should go in the agenda of this session. We will cover the Confluence Cloud architecture. We will share our challenges for architecting for scale. We will talk about how we do reliability at scale and how we solve our problems and architect for resiliency. The next thing we will cover is performance. And finally, we will say how to balance cost with reliability and scale. Before I go into Confluence, I would like to take a moment to talk about Atlassian. Atlassian is an industry leader in building collaboration software for teams to unleash the potential for teamwork. Confluence is one of the products where you can document, create, and organize content. It is a knowledge base for teams to be more productive and unleash the power of teamwork. The following slide gives a 30,000 feet view of the Confluence architecture. Like most applications, it started with a web app with a file store and a database and was deployed on-prem. We moved to the cloud in AWS and a completely stateless multi-tenant architecture. So you can see that the code is not architected for cloud first. It is forked from the on-prem offering. The AWS environment helped us to build scalable, reliable applications with seamless deployments. To give you a context of our scale, we currently deploy our application in 13 regions of AWS. We serve billions of requests per day with extremely low latency requirements. This is a very high-level overview of the architecture where the user's request hits the global edge. And from there, we talk to services for user management, which is the authentication of the user, tenant management, which helps us route to the right shard where the tenant is located. While this seems really simple, there is a lot more complexity which goes behind the scenes, but this gives you an overview of how the request routing takes place. The box in the middle is the shard, what we call for the monolith. It consists of various AWS resources. We have AWS EC2 instances for serving the web server traffic. We have the database for handling the database queries, for viewing, editing, creating pages. We have the caches and the AWS SQS queues for doing the async work. We also have AWS EC2 instances for worker nodes, which we could consume from SQS queues. The tenants are placed in the shard in a region which would be optimal for their performance. To minimize noisy neighbor issues, we do limit database connections in a multi-tenant environment per customer. So with this overview, we shall now talk about what were the challenges which we ran at scale and how did we go around architecting for those challenges. So the first issue which we faced was, since this was a legacy code base, not architected for the cloud, we ran into noisy neighbor issues. As we packed more tenants in the shard and in the database, we would see issues where requests from some tenant could impact the CPU of the database and eventually affect all the other tenants which are packed on that database in that shard. So we used to run into noisy neighbor issues. We would run into resource starvation issues. So there would be cases where the database connections, if not released on time, we would be blocking on those connections for a long time, and then other requests would not be able to be served. There would be cases where we had unbounded APIs and which would cause a high CPU utilization on our databases. At that point, we used Postgres as the database solution, and the only way we could scale was to go vertically. We also saw issues where a dependency service could bring down our system. So we were not resilient to any failures from dependencies. The other challenges we noticed were scaling challenges during peak traffic. So as your traffic is ramping up, we would not have enough nodes to serve them. And even if we spin up new nodes, it would take us a longer time to get that and serve the traffic. So with these kinds of challenges, now where we are proud to announce that Confluence Cloud can now support 150K users on a single tenant. This is available on the Enterprise, Standard, and Premium Edition. So how did we get there from our early days and all the challenges which we ran into? These were the following changes which we were made as part of the team. One of them was we started looking at decomposition. Well, you know about the decomposition journeys. It takes a while, and we were successful in some projects in decomposing some of our content from the monolith into microservices. But it was still not enough. So we started looking at Amazon Aurora and to leverage the read replicas. So with Confluence's traffic distribution, we saw that it was good to leverage the read replicas for handling certain traffic. How we got about doing this is the Amazon Aurora has a master and a couple of read replicas. We looked at our traffic patterns and we saw which requests could handle the eventual consistency and could be directed to the read replicas. For those requests, we targeted the read replicas. For those which needed strong consistency, we targeted the master. With this kind of traffic distribution, we were able to scale out the read replicas as needed. So in the past, the web servers could scale out, but the database could only go vertically. With the changes to Amazon Aurora, we could now even scale out the database. This gave us a lot more levers for scaling, as well as it helped a lot of our reliability issues. So moving to Amazon Aurora from Postgres helped us also pack multiple more customers on the shard than we could do before. So it was a cost-effective solution also. The other issue where we could not scale properly for the peak traffic was resolved by multiple fixes. We started having a pool of warm nodes which would be ready to serve traffic just in case the peak traffic ramps up, so the nodes would always be there that they could serve the traffic. We looked at other scaling parameters, such as step scaling, schedule scaling, and that helped us alleviate the concerns of the scaling issues which we had during peak traffic. So now that I've talked about some of the changes which helped us to go to the next level of scale and eventually support 150K scale, let me also tell you about other process changes which we made. So as the teams were growing, the user bases were growing, and the complexity was growing, it was also necessary to introduce some processes in place. So we looked at having feature gates for all code changes. What this helps is that if tomorrow there is an incident, we could go and roll back that feature. This would help us work with these large teams where a lot of contributions are made and a lot of deployments are going in daily. We can identify the root cause and actually turn off the feature flag and reduce and minimize the impact. Also, we address the issue where our dependencies were causing outages for us by adding some of the industry-known standards, such as smaller timeouts, circuit breakers where possible, bulkhead patterns. So with that, we addressed the issues of dependencies. We also ran war games, which would help us figure out how a failure of a dependency can impact our experiences. And we made sure that our experiences could handle those errors more gracefully. So with that, I would like to cover some of the best practices which we adopt for scale and might help you. So as we are building new features, if a feature is going to put a strain on critical resources, such as the database, the queues, then we enforce having architecture reviews done upfront. These can identify the bottlenecks, we can share the information across teams, and we can plan for that next level of scale. So this has really helped us over time to get better at feature delivery, as well as ensure that we can plan for the right scale. We have constant monitoring on critical metrics. One of them is how we are placing our tenants. So the tenants may also grow in terms of user bases, and it might grow in terms of data shape. So sometimes the shard in which they are packed may not be the right one. So we are constantly looking at how the tenants' performances, are they packed in the right shard, and otherwise we move them around shards to give them the most optimal performance. We are looking at other metrics such as CPU utilization for the database as well as our EC2 nodes. So we can scale accordingly and make sure we are tweaking the thresholds at the right time. The other thing which we monitor is the database connections. We need to make sure that the database connections are under the threshold. If we see any expensive queries which are holding the database connection for a long time, we go and optimize those queries by adding the right index or trimming the functionality. So with this constant monitoring of metrics, this has helped us in achieving the next scale. We also have a very mature load testing environment in staging. What we do is take the data shape of the largest customer, try to simulate production traffic, and then test our features in our environment. This gives us confidence that the new features we build could be rolled out successfully to the customers, and it also helps us detect any regressions in scale. It is this load testing environment that helps us certify for the next level of scale. So in this case, we are already certified for 150K users in a tenant, and now we are working on the next challenges to go to the next level of scale. So with this, I covered how did we architect for scale. Now, after scale, the next thing which we would like to cover is how do you do reliability at scale, and how did we solve those challenges. So how do we address reliability at Atlassian? We have 4 core experiences for Confluence: viewing a page, creating a page, adding a page comment, and editing a page. With these 4 experiences, we also have a public SLA where we have to guarantee 3.5 nines of reliability every month. If we breach this reliability metric, we are eligible to give refunds to our customers. So you may ask, what does 3.5 nines of reliability mean for a month? Basically, your budget is 21 minutes of downtime. This is calculated using 2 parameters. One could be when your system is completely down, then that gets counted towards your reliability metrics. The second could be that your system is working, but you have failures which prevent the users from handling these core experiences. This is what I call experience failures. So this 21 minutes budget is factored in with these 2 calculations, the downtime minutes as well as the experience failures per tenant. So we are focusing on the end-to-end customer experience, and we are tracking these failures. We are making sure that we are insightful of the customer pain, and then making sure that our reliability metrics follow this threshold of 3.5 nines. And if there is a bad month where we have outages, then we are eligible to give refunds to our customers. So with this background, I would like to share some of the best practices which we have followed for resiliency and which have helped us. We focused on early detection and monitoring. So making sure when the issues are caught, They are first detected as fast as possible and then mitigated as soon as possible by good detection and monitoring. We are making sure that the metrics we cover are insightful of what the experiences the customer is running into and what are the errors. That helps us prioritize which fixes should we work on first. We have very clear dashboards to identify whether it's a tenant level issue, whether it's a resource level issue, whether it's a deployment level issue. That helps us address these issues as fast as possible. And the only way we can meet these targets of 3.5 nines of reliability is doing a thorough investigation on errors proactively every day. To give you a context, we deploy our front end multiple times in a day. The back end gets deployed at least 2 times a day. So with this constant stream of changes coming in, it is very important to focus on what are the daily set of errors and emphasize on fixing them. So the next topic which I would like to cover is performance. We talked about scale, we talked about reliability. The third parameter which you need to balance is performance. What do we do for performance? There are metrics which we monitor. One of them is the TTVC, which is the time to visually complete. Basically, it is a metric which measures how long it takes for everything on the page to fully render without visually changing. TTVC is an industry standard metric. So we are following the same. We have dashboards which will emit events, and behind the scenes we are doing calculations to figure out where are the gaps and where we need to do better. For folks may be aware that there is another metric known as CLS, which is the cumulative layout shift. It is the metric to measure the visual stability of the page. Basically, it helps figure out which is the unexpected shifts which occur during the life cycle of the page. For a user, these unexpected shifts can impact the experience and cause a jarring browsing experience. So there is an issue if we have too many elements shifting over time. How did we architect for performance? Firstly, as I mentioned, it was a legacy code base, not architected for the cloud. So we had huge sizes of JavaScript bundles. So the first thing we did was reduce our JavaScript bundle sizes. So that helps to optimize for the network, the evaluation, it helps on the CPU, and also the memory consumption. So with the reduction of JavaScript bundle size, it definitely gives a positive gain towards performance. React 18 is given great improvements for SSR streaming. And we have seen with selective hydration and streaming, you can see great performance gains. So we are already on the journey of SSRing some of our core components. And with React 18 streaming, this helps us improve our performance even faster. There are places where we can do parallel fetching. So for Confluence, we would be fetching the content, but there would be macros which need to be fetched. So we could parallelly fetch the macros along with content, and that can help improve the performance. The next thing is there are so many items in the workload to improve performance. How do we prioritize? So the way we prioritize is we look at traffic patterns, you look at the size of the viewport, and then you look at the TTVC metric. These kinds of parameters help us figure which is the best fixes which would move the needle faster for improving performance for our customers. And as I talked about CLS, moving and fixing the CLS helps in improving the interactivity as well as the TTVC. So these were some insights on how we architected for performance. Now, the fourth aspect which I would like to cover is balancing cost. There may be times when as we are building new systems, it may initially not be as cost efficient because till the systems mature, we may be over-investing in the infrastructure. But over time, you need to optimize for cost and at the same time, balance the scale and reliability. So here are some insights on how we've been doing that. So one way is to have clear metrics attribution from our microservices for the cost. So we review in our meetings per week where we will check what is the cost for every microservice. Did it go over? If that was the case, was it because of new features? Was it because of regressions? And then what will be the plan to optimize for those costs? We have special projects which are also aimed at cost reduction. Some of the projects which I could give examples would be where we would pack more tenants on this shard. We could reduce some shards and move those tenants across on other shards. Another example could be, could we compress the database and thus helping to improve the efficiency of the database? There could be other projects where we looked at the instance type and figured out, would there be a better instance type which could help serve our requests? Amazon also offers spot instances. Could we leverage that on weekends? So with all these different projects, we are also looking at the cost opportunity and figuring out which would be the best ones for the teams to prioritize so that we can make it cost effective at the scale and the reliability which we are operating. Now, as Atlassian has grown, it has also become important to not just work in silos. You need to share your successes with other teams. So that is another area which we are emphasizing. As teams make some progress on cost optimizations, it might be also relevant to share with other teams. So we use different forums, whether it is tech talks, blogs, or special meetings where we could work with other products and also help them optimize for cost and balance the reliability and scale. So we covered numerous topics today. We gave an overview of the Confluence Cloud architecture, the challenges which we faced, architecting for reliability, architecting for scale, and how we measured performance. We also talked about the balancing of cost and making sure that the reliability and scale do not regress. So with that, I would like to end this session. And there will be challenges across the way. There will be unexpected issues which do come up. So I would like to share with the audience that keep calm. Cloud is the way where you could get the scalable, reliable architectures, but there are investments you have to do to make sure that you could deal with the unexpected. So thank you, Monster Scale Summit, for giving me this opportunity to share our learnings. If you have any questions, this is the way you could reach me, and I would love to answer those questions. Thank you.